In this lecture, we look at the kinetic theory of gases. This is a microscopic view of a system. Thermodynamics describes what happens to a system as a whole, not looking at the individual parts. So the question here in the kinetic theory of gases is, how do the motions of the atoms of a system give rise to the pressure and temperature and other quantities we've been looking at in thermodynamics? So if we have a box and it's filled with millions and billions of atoms bouncing around, how does the motion of these atoms or molecules give rise to this pressure and temperature? Well, it turns out that there's not just millions and billions of atoms or molecules in the box, but often there are many, many more than that. The group that we typically look at is called a mole, and it consists of 6.02 times 10 to the 23rd particles. Quite a few particles. It's defined in terms of the number of atoms in 12 grams of carbon. Avogadro's number is another name for this number of particles. So capital N subscripted with a capital A is 6.02 times 10 to the 23rd particles per mole. Different materials have different molar masses. So 1 mole of oxygen is 16 grams, or 207 grams of lead is also a mole, or 18 grams of water is also a mole. We like to make things simple, so we're going to talk about an ideal gas. And one reason, because we don't want to have to do analyses that have to do with, that only do pertaining to oxygen or to lead vapor or to water vapor. We want something that we can discuss about that's more general. Fortunately, at low densities, all gases behave about the same. So as long as we keep the density low so they don't, the gases themselves don't collide too often, we can have an ideal gas law that says that the pressure times the volume is equal to N, which is the number of moles, times R, the gas constant, times the temperature. So R, the gas constant, is equal to 8.31 joules per mole per degree K, and N, little n, is equal to the number of moles. For a fixed number of moles, we would find then that increasing T means the pressure and or the volume must increase, is an example of how this ideal gas law works. Let's look at a more in-depth view of this gas law and ideal gases by looking at an under-pressurized room or laboratory room. Typically, a laboratory storing biologically hazardous materials is at a pressure 10% below the atmospheric pressure to help prevent leaks of the material. If an oven in the room raises the temperature from 20 degrees C to 23 degrees C, how much does the pressure in the room change? Well, what are the assumptions we're going to make? Let's assume that air is an ideal gas, so we get an idea of whether this is going to be a problem or not. We'll assume that the laboratory is sealed so nothing goes in or out, so that the volume is constant. And this also means the number of moles of air in the room is also constant. Okay, now we'll use the ideal gas law. PV is equal to nRT. And we'll rearrange it a bit so that the initial pressure is equal to the number of moles times the gas constant R divided by the volume times the initial temperature. And we can use it again for the final pressure. The final pressure is again equal to the same ratio in front times the final temperature. If we divide these two, then we have P final divided by P initial is equal to T final divided by T initial. And rearrange that again, we have that P final is equal to the ratio of T final to T initial times P initial. Now, one thing we need to be very careful about is that when we go plug in the numbers for this, that the pressure final is equal to the temperature in Kelvin, not in degrees C. So that we have to add 273 to the number above, to the numbers above, to get the appropriate temperatures. So we need 273 plus 23 degrees Kelvin is our final temperature, divided by 273 plus 20 times K, 20K, is our final temperature times the pressure, which is 10% below atmosphere, so 0.9 of atmospheric pressure. And if we plug in all those numbers, we find that P final is equal to 0.91 times atmospheric pressure, which is fine. If there's a leak in the seal, air should flow in and not out of the room. Now, there was a question of, when we talked about using temperature in degrees K, what would happen if we made a mistake and instead used temperature in degrees C to solve this problem? 3 divided by 20, and we'd find that the P final ends up being higher than atmospheric pressure because there's a 15% increase. So we have to be careful to make sure we use temperature in degrees K.